Imagine, due to global warming, Antarctic ice will follow the same negative trend of retreat and disintegration already observed in the Arctic. There is indeed mounting concern that global warming starts affecting the ice in Antarctica. As first indicators for that are seen the observations of the massive disintegration event of the Larsen B ice shelf at the Antarctic Peninsula in 2002 and the recent unprecedented retreat of Antarctic sea ice in spring 2016. Owing to the rather challenging access to Antarctica, especially in winter, very little is known about the current state of the Antarctic sea ice, shelf ice, and the continental ice sheet, besides data from high-up satellite observations. This, however, makes it difficult to predict how quickly global climate change will affect an irreversible trend of ice retreat and melt, leading to an accelerated sea level rise. Antarctic sea ice grows in winter, reaching its maximum extent of about 18 square million kilometers every year in September, which is the size of about the South American continent. And subsequently it melts in spring, having its minimum of about 2.5 million square kilometers in February. This annual cycle of Antarctic sea ice plays a very important role in the global climate because sea ice reflects sunlight 10 times more than open water, and therefore moderating the energy intake of the Earth. Now, the study of Antarctic sea ice, that is marine ice, has been the domain of oceanographers, climatologists, and geologists. And you might therefore wonder how a mechanical engineer, such as myself, can contribute to this field. Well, besides the influence of temperature, sea ice formation in winter and its breakup in spring is the result of the interaction with the rough Southern Ocean surrounding the Antarctic continent. The interaction of ice flows with waves and wind and the fracture of ice sheets can only be accurately modeled and predicted by means of fluid and solid mechanics. On the other hand, Antarctic shelf ice is at the interface between sea ice, meaning marine ice, and the ice sheet covering the Antarctic continent. It serves therefore as a safety belt, slowing down the continuous outflow of Antarctic glaciers into the ocean. The stabilizing and disintegration of shelf ice is the result of various mechanics-linked processes. So you start with surface warming, then ice melt and hydraulic fracture of ice, also the creation of crevasses from the horizontal movement towards the ocean, but also the melting of the buoyant portion of shelf from below, and finally break of the buoyant shelf ice tongue. At UCT, my engineering colleagues and I are analyzing shelf ice integrity and predict its future deterioration by solid and fracture mechanics modeling. However, the models used need to be parameterized based on observational and experimental data, which can only be obtained in the field in Antarctica. For this purpose, field campaigns to the Antarctic have been undertaken to carry out ground-penetrating radar and geodetic surveys and monitoring of the shelf's internal structure, the bedrock underneath, and its annual horizontal movement into the ocean, as well as the opening of ice crevasses and faults. Furthermore, ice cores are extracted to ascertain the annual snow deposition and compaction, to analyze the crystal structure of the ice, and also to test the mechanical strength and stiffness of the ice material. The ice core analysis must be done under controlled sub-zero temperature conditions in a mobile polar lab moored aboard the SA Agulhas II, South Africa's icebreaker. In summary, global climate model predictions currently have to battle to give accurate answers on the future temperature and sea level rise. In order to improve these global climate models, an accurate prediction on Antarctic sea ice extent and shelf ice integrity are therefore important keystones. Thank you for watching.